Good afternoon, guys. This video is going to be a demonstration of how you can do a dynamic power rollup using Cameo Systems Modeler. This is based on MagicDraw version 19 with the Cameo Simulation Toolkit, which is what makes it Cameo Systems Modeler when you add in the systems modeling language plugin as well. So what we'll start out with here is a simple architecture that has a system block, a subsystem, two subsystems, subsystem A, subsystem B, and each one of those subsystems has two components. And what we're going to demonstrate in this video is how you can apply a rollup pattern to this architecture that will allow you to simulate the power usage of each one of these components depending on whether or not they're in an on or off state. And in your practices, you may have different states. Besides off or on, you may have a hibernate state or something like that, and I could show you how you could actually add those in as well if you'd like to simulate these different states that are using different amounts of power and different components running at different times. So the first thing you should do is go to your containment tree, and if you look at your options, you can show auxiliary resources. And then if you expand your MagicDraw customization for SysML package, what you'll see is you have a few analysis patterns in here and a few different types of rollup patterns. One of those is the power rollup pattern. So if you highlight the power rollup pattern as well as the constraint that is named total, I'm going to hold Control down and click on both of these. You can right click and go to copy or Control C. What we'll do is we'll paste these into a new package and we'll do a little bit of customization to these. So I'm going to go ahead and get rid of the auxiliary resources, and in the model just create a new element and it'll be a package, and we can call this the power rollup. And then I'm just going to hit Control V on that package, and if you expand it out, now you see you have the power rollup pattern as well as the constraint. This block named power rollup pattern comes with a parametric, and that is what does the recursive rollup for each of these, whether or not they're in different states, and it just totals up the amount of power that we're using, which we'll define in a little bit. So that is a parametric that comes with that block. It has a few value properties. We're going to add a few more value properties to that, and they'll be the names of the states that we create. If you notice, you also have this constraint here, and that's what shows up in this parametric. So you have total equals parent plus sum times child. And what we're going to do, if you notice, you have power that is typed by real, which would work in practice. However, I'm going to show you how you can make that a different type, and we can type that as watt instead of real, which might make it a little bit more realistic, because most likely you'd be using a value type of a watt or something to that effect. So let's go back to our block definition diagram. If you drag this rollup pattern block out onto your diagram, as well as the constraint, what you can do is click on the value property named power, and then if you see here, you have the ability to change the type, and we'll search for watt. And we can uncheck apply filter, and you have the option there for a power watt, which is what we're interested in using. And we'll do the same thing for the total power. So we'll change the type to watt. And we'll do the same thing for each of these parameters in the constraint. All right, so we've changed the type for the rollup pattern, but the other thing you should do is also change the name of this, because as of right now, you have two instances of this block in your model. So we'll name one of these Dynamic Rollup Pattern. And then we'll just do a soft delete on these to take them off of the diagram. They will still exist in your model, but they'll be in the containment tree and not displayed on the diagram. Okay, so the next thing you need to do is create a state machine inside of that Dynamic Rollup Pattern block. So to do that, you can right-click on it and create a diagram. And then you'll create a state machine diagram. For this example, we'll just do two different states. We'll start with an off state, and we'll have an on state. And what you'll see in a minute is how we can apply different amounts of power usage per component depending on whether or not they're in on or off states. So then we'll name the transition from off to on. We'll call that turn on. And then we'll do a transition back to the off state. And if you just click on that transition, you can type and it'll create a signal in your model. So if you notice in your containment tree now we have a signal for turn on and a signal for turn off, and that is what will allow us to trigger that transition between off and on. So I'm just going to hit a quick diagram layout. All right, in these states now, what you need to do is add an opaque behavior, which is going to be a simple JavaScript, and it'll say that when you're in the off state, power equals off, and then when you're in the on state, power equals on. So if you click on the state and you right click and go to the specification, if you scroll all the way down, we're going to add an entry behavior. From the drop down menu, you have a few different options. The one you'd like to use for this is the opaque behavior. So again, we went to the specification, scrolled all the way down, entry behavior, and then you're using an opaque behavior. And then in the body and language section, notice this is different from the body or the language section. You want to use the option that has body and language, and then hit the ellipsis to expand that out. And then you need to change the language to JavaScript. So in the drop-down menu at the top here, you can use JavaScript, and we'll type a simple script that says power with a lowercase p, because that will reference the value property that we have named power, and we'll say equals off. And we'll use an uppercase O because that's how we define the name of the state. So it's referencing the name of the state. Power will reference the value property called power. And that's it. That's your simple JavaScript. So you say OK on that, you close that out, and then close that again. So the entry behavior when it gets to the off state will be power equals off, and they'll do for the on state the same thing. So right click, go to the specification, all the way down to the entry behavior, use an opaque behavior. And then for the body and language, we'll say that power equals on, but let's change the language to JavaScript first. We'll say power equals on. And notice I used the wrong case for power. So we'll use a lowercase p for power, uppercase O for on, because that's how we define the state. And you can say OK after that and close that out. All right, so now the next thing you need to do is actually add the names on and off to this Dynamic Power Rollup Pattern block, and you add them as value properties. So you could do that in the containment tree here by right-clicking, creating an element, and using value property selection there. But you could also drag this block out onto a diagram and add it here. I personally like editing these on a diagram, so you can use these smart manipulator options that you have, but it does the same thing. So you could do it in the containment tree, or you could drag that onto a diagram and edit that. Either way will work, just depends on how you prefer to do that. So I'm going to drag that out, and we'll create an element, and we'll do a value property here. And for the value property, we will name one of them off and one of them on. So we'll do a capital O, and then we'll add the other value property, and we'll name it off. Now what we can do is go in and type these as power watt. So you click the T there, and we'll search for a watt, and do a power watt. And same thing for the off state. All right, so you should be good to go there. Now we'll do a soft delete on this to remove it from the diagram. The next thing you need to do is apply the rollup pattern. So to do that, you click on the highest level block that you would like all of this to roll up to, and we'll right click and go to Tools, and then you go down to Apply Rollup Pattern. Now if you look at the drop down menu, what you'll see is that you have the option for the dynamic rollup pattern that you customize. The one that is down here is the one that was in the auxiliary resources that you started out with, but since you added one, it now shows up in this drop down menu, and you can select that from here, and then we'll just go ahead and say okay. You can leave these options how they are. And now if you notice, it says subsets sub power, and if you'd like, you can always go in and just do soft deletes on this if you don't like them displayed. But for now, we'll just go ahead and leave that. So the next thing you want to do is run a simulation. And what we haven't done yet is actually told our system how much power it uses, whether it's on or off. But what we need to do before we do that is run this simulation, because we're going to define those in an instance table. So we're going to first right click, go to simulation and run, and then we'll hit play. Now if you notice, you have all of these state machines that just started up. So you have a state machine for component 1, component 2, subsystem A, component 3, 4, subsystem B. And what you can do is tell each of these individually to turn on or off. So let's say we wanted to go and turn on subsystem or component 1. You could click on that there and send the trigger to turn on, and then you notice you have component 1 on. But before we get into that, again, what we need to do is actually define how much power they're using, whether or not they're off or on. So if you click on the top level system block, what you can do is go to Export to New Instance. So you'll want to export this top level system block to a new instance, and then you just tell it where you'd like to save this instance. So you could create a new package in this window if you'd like, but we'll just use the Power Rollup package that we've created, and you can say okay. And then we'll just go ahead and stop this simulation. If you notice, we have this instance now in our containment tree that is named system. So the next step that you need to take is to create an instance table to where you can display this information and edit it. So from your model, if you create a diagram, you can search for instance table, and then you need to set the classifier. And for the classifier, you want to use the dynamic rollup pattern block. So we'll drag that in, and then we'll also set the scope. And the scope is the package that contains this instance. So we'll go ahead and drag that in as well. And as you see now, we have nothing but zeros showing because we haven't defined any of the usages for the power yet. So I'm going to go ahead and just hide these two columns because we're not that interested in those. So if you right click on those, you can hide them. What we are interested in is the on and the off state. So realistically, power would not be using anything in the off state. So let's just go through and define some numbers for these components in the on state. So let's say that component 1, when it is on, uses 2 watts, and component 2 uses 4 watts, component 3 uses 6 watts, and we'll say component 4 uses 7 watts. All right. At this point, what you can do is run a simulation again from the instance, and then when it transitions to one of these on states, it'll actually start totaling up the amount that they're using. So if we have component 1 on, you'll be using 2 watts. If we add component 2 on as well, you'll be using 6 watts, and so on. So to do that, you now want to run your simulation from the instance. So you click on the instance, go to simulation, and run. And then you can hit play. And now let's say we want to turn on component 1. Before you do that, what you'd probably want to be tracking is the total power usage. So let's say you want to see that in a time series chart. You can right click on that and say show in time series chart, and then it asks if you'd like to load the simulation profile, so you say yes. And if you notice right now, we don't have any power being used. So let's go ahead and turn on component 1. So if you expand out subsystem A, you notice component 1 is currently off. So let's send the turn on signal to component 1. And component 1 turns on, and you're now using 2 watts. And you see that also displayed here. And then let's say you want to turn on component 2. You can go click on component 2 here, and then send the turn on signal to component 2. And then if you notice now, we're currently using 6 watts total, which was the component 1 plus component 2. Let's go ahead and turn on component 3. And then we'll turn on component 4. So that is how you can dynamically simulate how much power you are using depending on which of your components or subsystems may be using power at the moment. As you may know, a watt is a joule per second. So what we're currently saying is we are using 18 watts, which is 18 joules per second. Now, realistically, you may want to track how many watt hours you are actually consuming, because a lot of times batteries will either you might report how much a battery could use or hold in either watt hours or amp hours. So in order to do a little conversion like that, what I'd first like to show you is how you can actually total up the amount of power you've used over this period of time. Because right now what we're showing is how much power we're using every second. But what we're not showing is the total power that we've consumed over this period of time. So if you'd like to add in a little bit more to your model to show how much power you've used over time, what you can do is add in another line to your JavaScript here. So let's go back to the state machine, and we'll add in another line. So if we go back to the off state, we will go to the specification and back down to the body and language section, expand that out, and we'll just hit enter here and do another line of JavaScript, and we'll say that total power consumed equals total power consumed plus total power. And remember, total power is already defined in our constraint or in our dynamic rollup pattern. It's a derived property. So we already have that value property defined. What we're doing is adding in another value property that we're calling total power consumed. So we do need to go back to that block now and add that as a value property. But this is the line of code you would add in order to make this work. And then the other thing we'll do is do a transition to self. So every 1 second, we'll do this calculation. So we'll click on the off state. And if you type a transition to self, you can just, on that line, start typing the word after. And we'll say after 1s, which will be after 1 second, you'd like it to come in and do this calculation again. So we'll add total power to our total power consumed every 1 second. We'll do the same thing for the off or the on state. The reason you may need to do that for the off state is because some of these components may be off, some of them may be on, but you'd like to run this calculation no matter what. So we're going to add it to both the off and the on state. So in the on state, you can go into the specification, you'll type the exact same code in the on state. We'll go back to body and language. And then we'll type total power consumed equals total power consumed plus total power. And you can say OK on that. And now let's go ahead and add that as a value property, the total power consumed as a value property to the dynamic rollup pattern. So we'll just go ahead and do that from the containment tree this time. So if you right click on it, you can create an element and go to value property, and we'll say total power consumed. And then we'll go to the specification so that we can type that as a watt as well. So if you go to the type, we'll search for watt, and we'll do a power watt and close that out. Now what I haven't done yet is added in the transition to self. So in that state machine, you'll do the transition to self and just start typing after 1s in parentheses. And we should be good to go there. So now when we run this simulation again, remember, run from the instance. So you can right click on that and do a simulation, go to run. And then when you play that, what you can do is then, as we did before, you go to the component, send that on signal, or before we get to that part, we can track the total power so you can show in time series chart. And this time we'll also add in the total power consumed. So we'll track total power consumed and do a time series chart for that as well. And now let's turn on component 1. And we'll turn on component 2. Notice you're getting a little bit of glitchiness happening here. And in just a moment, I'll show you how you can overcome that. So it's not allowing me to send that turn on signal because it's doing both of these transition to selves at the same time. So what we can do is create a graphical user interface where we can actually send these signals and it'll work a little bit better. But before we get to that, let's look at what we have happening now. So we have component 1 is on and it's consuming a total of 2 watts. And then our total power consumed is actually adding that 2 watts every 1 second. So we've now consumed about 90 watts of power, which is a good thing to know because a lot of times, as I mentioned, you may have a certain battery capacity or a certain amount of energy that battery would hold, and once you hit that threshold, you're out of power. So, so that would be a very useful thing to do. In just a little bit, I'll show you how you can convert that to watt hours instead of what we have right now, which would be more like a watt second or 1 joule per second. So let's go ahead and stop this simulation. So in order to overcome that glitchiness that you saw in the simulation window, what you can do is create a graphical user interface where you can send those signals from that instead of using the signals in the simulation window. So in your model, if you create a diagram you can search for user interface, and it's a user interface modeling diagram. And then in this diagram, if you drag a frame out, you'll actually need to drag out one frame for every component that you'd like to send a signal to in the simulation. So we'll drag 4 frames here. And then all you need to do is drag the components onto these. That way it'll have access to those components through the frames. So we have component 1, 2, 3, and 4. So I'll drag component 1 to this frame, component 2 here, component 3 here, and component 4 here. And then we can reuse that same turn on and off signal, and it'll know which component or which block to send that signal to. So we'll go ahead and we'll drag the turn off signal and the turn on signal to each one of these. Now at this point, if you were to run that simulation, it would not actually activate this graphical user interface. So you have to associate this GUI with this simulation. So to do that, you create a simulation configuration diagram. So in your model, now you'll create another diagram, and you can search for simulation, do a simulation configuration diagram. And then the first thing you'd like to do is set the execution target. So we'll use this system instance, the same instance we've been using. You can drag that onto the simulation configuration. We'll go ahead and give this a name, and we'll call it a Power Rollup. And then you need to drag each one of these graphical user interfaces onto that simulation configuration. So we'll drag component 1, component 2, and component 3's GUI, as well as component 4's. Now, when you run the simulation from here, it'll start up each of these graphical user interfaces with that simulation. The other thing we could do is set the time series charts to automatically start up as well. So let's say we wanted to, when we started this simulation, also start those time series charts that I was doing from the simulation dialog. You could do that here, and then you wouldn't have to do it through there. It would automatically start up as well. So for this time series chart, what you'll do is drag the total power consumed value property here. And then we'll do another time series chart for the total power that we were tracking. And then for represents, let's say we will use the Dynamic Rollup Pattern block. And then each of these you can now drag onto your simulation configuration. So when you run this simulation, those time series charts will automatically start up for you. So now what you can do is just right click here and go to simulation and run, or you have the option in this drop down menu to just hit play from here. So let's use that, and we'll select play. Now what just started up on my other screen was both of these time series charts, as well as the graphical user interfaces that we created. So drag those out here. So now you have component 4 there, component 3 there, component 2, and component 1. If you notice though, what it looks like happened here is we have the total power was for a specific part of the system. So we got a total power for each of these, which may not be what you would want. So let's say we just wanted to track the ones that were for system. If you notice it says system here, this one's for subsystem B, this one's for subsystem A. So I'm just going to close out some of these and get rid of those. It may be best to just start those up during the simulation so that you don't end up with so many different windows like that. So what we have here is the total power consumed for the system and then the total power for the system. All right, so let's go ahead and send these signals to turn on these components now. If you notice, this is giving me a little bit of trouble even expanding the window. So I'm going to go ahead and just stop this simulation now. I'm going to go back and get rid of those time series charts. So let's go back to the simulation configuration diagram, which is this one here. And I'll just do a hard delete on these. And then we'll run this simulation again. So simulate. Drag this window up just a bit if I can. There we go. And then we have the GUIs over here, which we'll drag back out. All right, and then from the simulation window, we'll start up the show in time series charts for the total power as well as the total power consumed. And we're ready to go. So we'll go ahead and send the turn on signal to component 1 and component 2 and 3 and 4. So if you notice, the total power that we're using every second is 18 watts, and then the total power consumed continues to climb because we're using 18 watts per second, and it's adding that every 1 second, as we're telling it to do with the state machine. So that is a great way to do a simulation like that, where you can dynamically turn on or off different parts of your system. But as I mentioned before, you may want to also convert that to watt hours instead of what you're currently looking at, which is watts per second. So to do that, what you can do is add a constraint. So we'll go ahead and stop this simulation. We'll go back to the block diagram. So the block definition diagram, and we'll go ahead and drag that Dynamic Power Rollup Pattern block back out into the diagram. And let's add another value property to this, and we'll call it total power consumed in watt hours. And we'll just do WH, and then let's type that as well. So we'll go to type, and watt hours is not going to be an option. So what you can do is go to the specification. So I just double clicked on that value property, and then for this we'll type watt hours, and I'll just click off of that. It gets a little tricky making new value properties in here, but I clicked enter, and then that accepted that. So now we have a new value type that is called watt hours. And in order to convert the watt seconds to hours, what we'll do is create a constraint. So we'll use a constraint block, and we'll call it total power consumed in watt hours. And then for the constraint, you can say total power consumed, WH, equals total power consumed divided by 3600. And then you want to go ahead and display those parameters, or parse and create parameters. So if you click on the constraint, use this option here that says parse and create parameters. And now you have parameters, which are essentially they look like ports when we get to the parametric, but they're where it takes in those value properties. So what we'll do before we do that is drag the constraint onto the block, That way it will own that constraint. And then let's go to the parametric diagram now for that block. And if you drag the constraint in from the containment tree, you can just drag that out. What you can do then is display all parameters. So those are the two parameters that we created. One, total power consumed, and the other one is total power consumed in watt hours. So now what you can do is display value properties, and it'll display any value properties that are owned by this block, which is Dynamic Rollup Pattern, that are not currently being displayed on the diagram. So if you go to display and then value property, these are the other value properties that we have over here that were not being displayed, but we're not concerned with the off, so we'll do a soft delete on that. I'm not concerned with the on. What we do want is total power consumed and total power consumed in watt hours. So let's go ahead and create a binding connector to that parameter for each of those. All right, now when we run this simulation again, what we should have is something that converts total power consumed into watt hours. So what we can do is just from this drop-down menu, select Power Rollup and then click play. And then if you notice, let's go ahead and we'll send the turn on signal to one of the components. What we have in our simulation now is a new value property that we've named total power consumed WH, and it's typed by watt hours. So our total power consumed, which I mentioned before, is essentially watt seconds, is now being displayed in watt hours as well. And then if you wanted to take it a step further, you could use a similar process to go in and convert that to amp hours. And I leave that up to you guys to do. So if you guys have any other questions about how you may add that in, just let me know. Send me a message and I'll be happy to help out. I hope this was helpful. If you have any other questions, please feel free to reach out.